I will challenge myself. This may be the hardest thing I've ever done, because I literally didn't know that I'm going to speak until 50 minutes ago. So I had no time to prep, and this is a complete jam. I'm going to talk about the difficulty of scaling stuff to very high numbers, like connected car. And since I've been, I'm taking that slot from the wonderful Sarah Cooper, who works for AWS, and I work on Azure at Microsoft, I will therefore refrain from product pitches, just to be fair, except I'll give you some numbers. But those will be technical numbers, so I'm not going to talk about business value and any of those things. So that's the first thing. Second, since Andy might be totally nervous about me speaking, Andy Stanford Clark, are you still here? There you go. I'll start I start this with a quick story, because all talks need to have some historical insight, obviously. Do you know IBM SAGE? Yes, so IBM SAGE is the semi-automatic ground environment. And if I had known that I would speak, I would not be wearing a Cold War airplane shirt, as I do now, the Avro Vulcan. And the semi-automatic ground environment system was the greatest computer system built in the 50s. And it is the first IoT system in the world. And what it was built for is the United States were a little worried that the Soviets would show up with airplanes and bomb their place into oblivion. So they had to do something about it. So they built a staggering array of radar stations. Some of them, called the Texas Towers, were actually sitting right in the Atlantic, very, very many miles offshore, so that they'd be closer to the anticipated incoming bombers. And that semi-automatic ground environment was spread around the entire States, and was a connected system of IBM mainframes set up in 4-story buildings that were really enormous. And they were the biggest computers in the world at the time, specifically built for that system, and then interconnected with a network to create an early warning system. So that was that first system, the first IoT system that was built. And that first IoT system had exactly the same scale problems and challenges that we are facing today, because we haven't done this before. We talk about the connected car. And we talk about the connected car as if that was something that was a solved problem in just terms of sheer scale. It's not. So yeah, you can buy today for your BMW the connected drive, I think. And you can buy for your Audi also the connected, I don't know what it's called. I have it, but I can't remember the name. You can buy internet connected services. But those internet connected services come behind a very, very stiff fee. And that stiff fee is, from my Audi, I know that fairly precisely, about 5,000 euros. I have to get options, the entertainment system, and then the extra option for the entertainment system, and then the extra option of the entertainment system, plus 500 euros, so that I can get that capability. That means it doesn't sell well, and that's by design, right? So what you hear today about connected cars is either loosely connected, so they do make some HTTP requests here or there, or the client populations are really in the tens of thousands and not in the millions that they are actually putting on the roads. So millions is hard. So I'm going to, the visuals are going to be very sparse, because obviously no slides, and if I get fired, I don't want to get fired for the slides. So that's the universal symbol for device. And this is the universal symbol for the cloud. And all my friends always make fun of me, because I always put the cloud on the bottom. So that's the link we're talking about. Connected car is not a peer-to-peer problem, as many other problems are. There are aspects to peer-to-peer, vehicle-to-infrastructure, vehicle-to-vehicle communication. I'm going to forget about those. Let's talk about predictive maintenance. Let's talk about data that flows out of the car. Let's talk about the car getting information from the cloud. And let's talk about cases where you want to go and execute some action on a vehicle. So you use your smartphone as a device to go and control your vehicle. Let's go and take a few functions for that. First function would be to remote lock. You get out of your car, you walk away from the car. Now you're in the store and you're like, did I lock my car? Like your key's too far, right? And now you're wondering, did I lock my car? Well, remote lock is great because you can get a status and go and do some action. How does that work? You need to have a connection. So cloud to device is this. And this is where it gets dicey. We know how to do this very well, HTTP, right? Problem solved. As long as we only need to go and fire data from a device to a cloud system, we have a solved problem because that looks just like the web. You still need to be clever about the stuff that you do on the bottom. I can get to that later, I hope. But that link, the ability to actually go up, poses the first very significant scale problem that is unique to the IoT. Because that's not a web problem. What do we need? We need to have addressability. We need to have support for roaming, right? This car here will ultimately be connected through some carrier infrastructure. And it hops towers. And you're going to have roaming. And you're going to have roaming through different IP spaces. Because you're going to have, in M2M, you can do local domestic roaming across carriers, which is not allowed on voice. In most countries, but you'll get this on M2M contracts. So there is not a single IP address you can rely on, right? There's nothing on the network that actually allows you to stay on that. But you still need to be able to go and route to that device. So what do? Well, you put a little mailbox onto the server. That little mailbox is representing that device in the system. If you want to send something to it, you want to send the remote unlock code, right? It ends up in that little queue. And then when the device connects, it pulls that data up. And this system never needs to know what the address of that device is. What you do is you create a connection, and it pulls the data up. Now, that connection is something that you want to keep alive for as long as you can. So while you're on that tower, you will go and maintain that connection. And as soon as something shows up, you want to go and send that up. Scale. What's interesting here is that we now need a system at the bottom if I have 1 million cars, I need to have 1 million little queues. And 1 million little queues are hard. How do you size those? How much capacity do you have for those little queues? 8 KB? 2 megs? Those queues are interesting because they need to have low latency, right? If you want to unlock the car, you want to have it perceptibly imminent, as I call it. So you push a button and the car opens, which means latency must be very low. The runtime you can allow through that link here is a few milliseconds, right? At most 2 seconds for that entire track. So you need to be fast. So those queues need to be, they can't be heavyweight things, and they also need, as I said, they need to scale. So that's one problem. Another problem is, how do you design the gateway? Because if you have little queues, we actually can't do this. Can I sit on this? Yes. We can't do this. This here, in reality, is many, many, many machines. So what we run in our systems is we run clusters. So for our messaging systems, for instance, we run clusters where we have 128 beefy quad-core front-end machines and 128 beefy quad-core back-end machines that make up one broker. 256 4-core machines making up one broker. It's one thing. Looks like exactly one thing to everybody, but it's internally split up like this because otherwise we wouldn't be able to take that load. I can't send this car to its little queue, because that queue may move, that machine may be down. There's all kinds of reasons for that not to be the case. So what I'll do is I'll put a gateway in front of this. The gateway is my abstraction for that system. The gateway does handle protocol, and it's actually optimized for the case of connectivity, because connectivity itself comes with cost. TCP was mentioned already. TCP versus UDP. UDP is lightweight, yes. UDP doesn't cause so much work on the device, yes. But it's an awful protocol for doing anything over the internet. Multiple reasons. First, it's lossy. So there's no guarantee, so the packages get lost. The second is you can't throttle it. When you use TCP, TCP is supported by the lowest levels of the networking stack of your operating system. If something comes out of order, if a packet is unexpected, the network stack will toss it and you will never see it. In UDP, that bubbles straight up into your app, outside of kernel land, in user land, and you have to go and deal with every single package, whether it's malicious or not. Not good. TCP is slower and is impacted by latency, etc., but it's a more reliable protocol. TCP has costs because TCP works like a ferry boat. You put packets on a boat, you send them over the lake, boat comes back, everything okay, next packets on the boat, send them over the lake. Boat sinks, you had too many packets. Take new boat, take the half of those packets, send that across the lake. That's how TCP works. It's a fairly reliable thing. The packets that you put on that boat, the number of packets you can put on that boat is called the buffer. That buffer, the receive buffer, lives here. If you have 1 million connections, you need to have 1 million buffers, which means if all of your things go swimmingly well and you could use TCP window scaling and all the wonderful things, and all of your, the socket cost for a single socket would be 1 megabyte. It's 1 million times 1 megabyte that you just need to keep those sockets open. Memory impact. And some CPU impact, but that's actually that's not as important. So that's something to think about. There's actual hard costs to maintaining those sockets, but it's not, UDP is not an alternative, because that just makes you a giant big target for denial of service attacks, which we obviously are a happy target for because we're Microsoft. So that's hard. How do you partition the gateway? The gateway itself is also partitioned. We have to think about that as well. So we want to have these reliable, effectively, we want to have these nailed up connections. Someone comes and makes a connection to us using MQTT or AMQP or WebSockets with some naked JSON on top of that. So we want to maintain that connection because we want to send stuff up. And the only way how we can send stuff up is have that device having made the connection to us. Right? So now we're maintaining those. How do you manage that at scale? What is the gateway sizing? Well, there's people who say, well, I can do 1 million connections on my PC, on my server. And you can. The problem is, if you lose those 1 million connections in one snap because that machine goes down, you just set yourself up for a denial of service attack. And that's your own fault. Because all of those 1 million machines which connected to you over time are going to come up in one go right away because they just lost their connection. So you need to balance out maximum density you can achieve on a machine versus the density you want on that machine, because otherwise you're effectively going to have a denial of service against yourself. So that makes that hard too. What's also hard is, and that's what I need the numbers for, hang on. I have those here. I have those numbers here, and I'm going to write them down. Here they are. Okay. So, a few numbers. 99.999, what was it? 76. 76%. Reliability. So when we process, this is one of our systems, it's Event Hubs, it's called. Our operational reliability is 99.9976%, which is pretty good. Let's make this let's make this relative though. 3.8 T per week. We do 3.8 trillion transactions on that system per week. We do sustained in our system 24 hours a day, about 6.8 million transactions per second. If you now apply 99.9976% to that, that means we throw hundreds of thousands of errors per second. Because those distributed systems are animals, they are alive. Stuff goes down and goes bad, and there's compression in terms of resource usage. Requests get squeezed out, they get homeless because stuff switches in the back of the system. And we have 36 data centers over which we run those things, and there's deployments and there's changes happening all the time. Reliability and availability are core factors in making those things work. And that's actually the hardest work that we need to do. Not only do we need to make those millions of devices work, not only the scale, but also we need to make the reliability work. We need to achieve availability and reliability rates where 5 nines, we're at 5 nines effectively. Right? This number goes up and up and up, and we've had 5 nines, and 5 nines is kind of the gold standard where you want to be. But at the scale, 5 nines means hundreds of thousands of errors that we need to get rid of. So that's the quality work that we need to do in our systems to make that better and better and better and get to 6 and 7 and 8 and 10 nines, which is a lot of work for the future. It's really difficult to make those things. So, time is up. I hope that gave you a little bit of insight into the pain we're suffering while we're building these very large-scale backend systems, which is a perspective that you don't necessarily have when you build just the thing and want to connect it to the internet. Thank you.